this bicycle is moving from an initial position to a final position on a circular path, and then we know that this bicycle is turning an angle delta theta. This angle is known as angular displacement. And by the time this bicycle is moving on an arc, this is called in maths arc, and the distance traveled by the cyclist is called arc length and delta s. And as the bicycle is moving on a circular path and then traveling a distance of which is equal to delta s, it's also turning an angle which is delta theta. And we can define the speed of this cyclist by two ways according to the linear quantity. Remember, if a quantity is represented by distance, it is called linear quantity. But if a quantity is represented by angle, it's called angular or rotational quantity. So because it's moving on an arc and then length of the arc is distance, so this is a linear quantity, and arc length delta s is a linear quantity. By the time this bicycle is turning by some angles delta theta, and it's an angular quantity or rotational quantity. And we can even describe the speed of this cyclist by two ways. One of them is the linear speed. So this bicycle is moving on this arc, how fast it's moving or how slowly it's moving. So it is defining the linear speed, and in the 11th grade you learn about that when an object is moving in line and you define how quickly this object is moving. So you said its speed is greater, or how slowly it's moving, and you said its speed is smaller. And in the first chapter section, we also talk about how quickly it turns, rate of rotation. So it's known as angular speed. So in fact, these two speeds, their definitions are very similar. So to calculate the linear speed from here to there, when this bicycle is moving from here to there, from initial position to final position, you only divide distance by time. So delta s is the distance traveled by the bicycle. Delta t is the time interval from initial position to time final position. So you would divide them, you calculated them, and you did the same thing in many times in the 11th grade. And also in the 12th grade, in the first section, we defined another speed, which is angular speed. It is defining how quickly this bicycle is turning by how rate of rotation. Also, it's defined as delta omega average. Remember, it was delta theta divided by delta t. So their definitions, even their equations are very similar. And also, there is a relation between this linear speed and this angular speed. So there's a relation, mathematical relation between this linear speed and angular speed. You can also think that if it is moving faster from this point to that point, also it's turning with it faster with the angle. Yani angular speed and this speed, linear speed, are in fact directly proportional. If linear speed becomes greater, angular speed also becomes greater. If it is moving faster on delta s, it's also turning faster on delta theta. So in this section, section 2, we will get the relation between this linear speed and angular speed. How they are related, we are going to learn in section 2. So this section initially study how linear speed v and angular speed omega are related, and we will get this equation. Now, your book is defining study in this section by a carousel. So, you know, maybe we wrote a carousel. There are horses, and we are riding on horse, and these horses are turning together with the carousel. So because carousel is a rigid object, remember what does rigid mean? So its shape is not changing as it is moving or as it is rotating. Its shape is the same. So if for a rigid object, because carousel is a rigid object, all horses on the carousel will have the same angular speed, will have the same angular acceleration, will have the same angular displacement. Yani, if one of the horse turns 90 degrees, all horses turns 90 degrees. If one horse completes one revolution, so all other horses complete one revolution. That's why their angular displacements are equal. If one horse is moving with 5 radian per second, other horse also moving with 5 radian per second, because their angular speeds are the same. If they are speeding up, they are speeding up together. Their angular accelerations are the same. This is the very important sentence. Remember the last lesson of the first week, we talk about this. If an object is rigid, so this object will have absolutely, indefinitely same angular displacement. So every point on this object will have the same angular speed and same angular acceleration. Now, we will talk about these two horses. One horse is, I will say it is A, other horse is B. Initially, these two horses are side by side like this. And this carousel, assume that it's rotating counterclockwise. So it's rotating like this. So consider carousel turns counterclockwise. Of course, the position of these two horses will change. After some time, new position, I will say final position of these two horses will be like this. Because it's a rigid object, they will turn in the same angle. Yeah, and this angle, delta theta, angular displacement will be the same angular displacement of A and also its angular displacement of B. By what angle A turned, so the same angle B will turn. That's why their angular displacements delta theta are the same, because the carousel is a rigid object. But distance traveled by these two horses are not equal. So one horse travels a longer distance than the other one. Even their angular displacements, delta thetas, are the same. Even they turn with the same angle, but distance traveled by horse A and distance traveled by horse B are not the same. One of them travels a longer distance. Which one is traveling longer distance?
Horse B. B1.
Of course, B is longer than A. You see that A is shorter, B is longer. Of course, B is traveling a longer distance than A. So then we say that the horse on the outside, generally, the horse on the outside travels a longer distance than the horse on the inside one and outside one. The horse on the outside will travel a longer distance than the horse on the inside in the same time interval, delta t. So the horse on the outside is B in here, according to this figure. The horse in the inside is A. And this distance traveled by horses are called arc length. Remember, we defined them, delta S. Delta S. For A, I said delta S A. For B, I said delta S B. So this belongs to horse B. This belongs to horse A. Then horse B has a longer arc length than horse A. I can say that. So if these distances are not the same, but they are starting to move at the same time, again at the same time they are here, which means their time to travel from this point to that point and from this to point to that point are equal. Assume that there are your physical training teacher making a race with two students are racing, and then she's blowing a ring and then saying you run. One girl is traveling longer distance than the other one, so until teacher stops them, which means the one which travels longer distance is faster than the one which is traveling shorter distance. In here, then we can say that one horse is traveling longer distance than the other one in the same time interval, so then that horse must be faster. So which horse is faster according to the linear speed? Horse B. Horse B is faster, but according to linear speed than horse A. Why? Because horse B is traveling a longer distance than horse A. So outside, the horse on the outside will have a greater linear speed than the horse inside. So, but their angular speeds are the same. Don't forget, because they turn with the same angles. However, the one which is outside travels a longer distance than the one which is inside. For that is it's linear speed. Linear speed you define in the 11th grade. So linear speed of the horse which is outside will be greater than the linear speed of the horse which is inside. Yeah, no, horse B is faster according to linear speed than horse A. This linear speed, you define the line as linear speed. Now, in this section, will be given a new name. That name is called tangential speed. So tangential speed of the horse B is greater than tangential speed of horse A. So, or the horse on the outside has a greater tangential speed than the horse which is inside. As I said, tangential speed is a linear speed. It is the speed you study in the 11th grade. So you define the motion according to distance. If you define the motion of an object according to distance traveled by the object, so it is called linear speed. And if this motion is on a circular path, so now we are defining this linear speed as tangential speed. Why is it called tangential? Now we will try to get this, okay? So tangential speed is defined as, this is definition in your book, the instantaneous linear speed of an object along the object's circular path. Yeah, and if an object is moving on a circular path, that linear speed is defined as tangential speed. If an object is moving on a circular path like these horses, that linear speed is given a name as tangential speed. Why called tangential? Because their direction of the motion are tangent to the circle. So what does tangent mean? Tangent line. So what is tangent line in maths? Now we should first learn this. What is a tangent line? This is definition of tangent line in maths. Any line touching circle at a point. Yes, touching circle at a point here, 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 or here, or every point. So you can draw a line which touches the circle at that point, but that line is always perpendicular to radius. Look at here. This is the one tangent line. It's touching the circle in here, and this line, red line, is perpendicular to radius. This red line is called tangent line. Another tangent line you can draw from another point. Look at here. So this red line is touching circle at one point and perpendicular to radius of the circle. Yes, it's third tangent line. This line is touching circle at one point and perpendicular to radius. You can draw as many tangent lines as possible from these points. For example, let me draw one more with my pen. So I will draw a tangent line in here. So this is the point where I want to draw the tangent line. Draw a line touching the circle at that point and perpendicular to radius. So this is the rule, how to draw the tangent. So this is called tangential speed because these horses are moving at that moment tangent to the circle. Their direction of the motion is along this line. These horses are moving along this line. These horses moving along this line. That's why it's called tangential speed. Their directions are along that line, along the tangent of the circle. Tangential means along the tangent. Tangential means along the tangent. That's why their directions will be along the tangent like this. This horse at that point will be moving along the tangent of the circle, along the tangent to the circle. At that point, so when they advance to a new final position, they are still moving along the tangent to the circle. They are still moving along the tangent to the circle. So when these horses comes here, assume that this here is the new position. So this horse A will be moving like this, again along the tangent. Another point along the tangent again. Another point along the tangent. Yani at any time, these horses will be moving along the tangent to this circle. So that's why it's called tangential speed. So directed along the tangent to the circular path. And this tangential speed is greater with farther distance from the axis of rotation. Which horse has a greater speed, B or A? Of course B. I draw B longer than A, as you see, because it's on the outside. The horse on the outside is moving with a greater tangential speed than the horse which is inside. So that's why tangential speed of horses is proportional to radius of the circular path. In here, radius is shorter, but in here, radius is longer. Greater radius, so which means the horse with a greater radius, of course, will be moving faster. So that's why tangential speed is proportional to radius of the circular path. Tangential speed proportional to radius of the circular path. Even we can get a proof for this. It's possible mathematically to make a proof. So I will show it to you. You remember this equation, delta theta is equal to delta S over R. It is the first equation we studied in the section 1. Cross product, if you make cross product, so delta S becomes R times delta theta. If we divide both sides of this equation by delta T, time interval, you can do that. If you divide both sides by the same number or multiply with the same number, equality does not change. Delta S over delta T, remember it's called tangential speed. Delta theta over delta T is called angular speed. We learned that. So that's why tangential speed equation becomes R times angular speed. It is also says here, because these two horses have the same angular speeds, because it's a rigid object, omegas are the same, but tangential speed changes according to radius. The horse which is closer has a smaller radius, of course, smaller tangential speed. The horse on the outside, greater radius, because that's why it is a greater tangential speed. The horse which is farther from the center of the circle will have a greater tangential speed, because radius of the circle for this horse will be greater than the one which is inside. So this is the equation which relates tangential speed and angular speed. This is the equation which relates tangential speed and angular speed. If you multiply angular speed by radius, you will get the tangential speed of any horse on this carousel. So we will use this equation now in solving the problems. One problem, sample problem. The radius of a CD in a computer is 0.6 meter. This is a kind of CD. You know, right now we don't use so much CDs in the playing the or the music, listening to music, but in the past those devices were be using, for listening musics. Of course, it's a disc. CD, it's called a kind of a disc. It has a radius 0.6 from here to there. So that distance is the radius. So this radius, let me draw it. This radius is given in the question as 0.06 meters. R is 0.06 meters. And if a microbe riding on the disc rim means edge. Microbe is a bacteria or virus riding in here. So as this disc is, or this CD is turning or rotating, this bacteria or this microbe is also rotating together with the disc. The like horse are turning together with the carousel. This microbe is riding together with the CD. If the microbe is riding on the disc rim means edge of the disc is called rim, here, rim, and has a tangential speed of 1.88 meter per second. So this microbe is moving with a linear speed or tangential speed, which is equal to 1.88 meter per second. What is this angular speed? Calculate omega. So this CD is also rotating with some angular speed, so calculate this angular speed. So radius is 0.06 meters, so which means this microbe is moving on a circle whose radius is 0.06 meter. It's moving on a circle. So this is a circle followed by the, let me draw that circle. This is the circle followed by the microbe. So like this. And this circle has a radius which is equal to 0.06 meter. And tangential speed of this microbe at any point, for example, in here, this tangential speed Vt is 1.88 meter per second. So calculate angular speed of this CD, calculate omega. We know the equation. Vt is equal to R times omega. Vt is equal to R times omega. You know what R is, you know what Vt is. You can easily calculate what omega is. Divide by R and simplify R, because you need what omega is. Simplify R. Omega is equal to Vt divided by R. Omega is equal to Vt, tangential speed divided by R. Tangential speed is 1.88. R is 0.06 meters. Divide them. So then this CD is turning or rotating with an angular speed of 31.3 radian per second. This is the answer of this question. If there is a tangential speed, there also must be a tangential acceleration. There also must be a tangential acceleration. When carousel rotates with constant angular speed omega, the horse moves with constant tangential speed. The horse moves with constant tangential speed because we know that V is equal to R times omega. If omega is constant, which means tangential speed of this horse also must be constant because the same horse moving at the same radius. So R is the same, omega is the same, V is the same. Okay, if this carousel is speeding up or slowing down, if this carousel is speeding up or slowing down, look at here. Initially, it's moving with an angular speed omega initial. Then speeding up, it is speeding up. Let's write speeding up. So then this angular speed must increase from an initial value to a final value. By the time tangential speed also must be increasing because we know that tangential speed initial is R times omega initial. A tangential speed final is R times omega final. If omega is changing, these tangential speeds also must be changing. It must be increasing together. When carousel accelerates with constant angular acceleration alpha, so we defined this alpha before, remember? So it was omega final minus omega initial divided by delta t. The horse also accelerates from an initial tangential speed to a final tangential speed. Now we can also write an equation about the linear acceleration. It's possible. Along the circular path, the horse also experienced an instantaneous linear acceleration. This horse is speeding up, yes, from initial speed to a final speed, yes. So then there must be a linear acceleration too. As you studied last year, you defined last year. We can give a name to this instantaneous linear acceleration as tangential acceleration. Yani this horse will have a tangential acceleration, linear acceleration along this circular path, and name of this acceleration is tangential acceleration and represented by AT. Okay, so can we get the equation for this? Yes, we can. First, I will define it. What is tangential acceleration AT? It is defined as instantaneous linear acceleration. Its definition is very similar to tangential speed. Remember, in tangential speed, instantaneous linear speed of an object along the object's circular path is called tangential speed. Instantaneous linear acceleration, instead of speed, you are going to write acceleration. Instantaneous linear acceleration of an object along the object's circular path along this circle is called tangential acceleration. And this tangential acceleration also will be directed along the tangent to the circular path. Yeah, it's directed along tangent to the circular path. So we know how to draw the tangent. Yes, we learned. This is tangent line, AT is along the tangent. When horse comes here, AT is again along the tangent. When horse is in here, it will be again along the tangent. So this tangential acceleration will be along the tangent line, and we know that this tangent line is always perpendicular to the radius. And it is defined also as the rate of change of tangential speed. What is changing in here? Tangential speed is changing. Initial tangential speed, a final tangential speed. Tangential speed is also changing. For that, it's also defined as the rate of change of tangential speed in tangential direction of a circular motion. So tangential direction, tangential direction, tangential direction. If tangential speed is changing along the tangential direction of the circular motion, so we can calculate tangential acceleration. And getting equation is the same. This is, remember, the general definition of acceleration. Tangential acceleration, AT, is equal to change in tangential speed divided by time interval. A tangential speed is what? Remember, we know Vt is equal to R times omega. If omega changes, tangential speed changes. If tangential speed changes, omega changes. So we know that. So that's why instead of delta Vt, I will write R times delta omega. And if I divide delta omega by delta t in the first section, we know that it is called angular acceleration. It's defining the angular acceleration. That's why tangential acceleration will be also radius times angular acceleration. Remember, in tangential speed is equal to r times omega. Tangential acceleration is r times alpha. Yani angular acceleration multiplied by radius is tangential acceleration. Angular speed multiplied by radius, tangential speed. Their equations are very similar. So then I can say that if I know what angular acceleration of an object is, I can calculate the tangential acceleration of any point on this rotating object. And if this horse is speeding up, which means final speed will be greater than initial speed. If speeding up, final is greater than initial. So that's why delta V, change in speed, will be positive. That's why object will have a positive tangential acceleration. So tangential acceleration will be positive if the object is speeding up, because final speed will be greater than initial speed. But if negative, if tangential acceleration is negative, which means final speed must be smaller than initial speed. That's why object is slowing down. So by looking at the value of the tangential acceleration, you can understand if an object is speeding up or slowing down. For example, if a question says you tangential acceleration is negative 2 meters per second squared. So the object is speeding up or slowing down. So because this is negative, so which means there's a final speed is smaller than initial speed, so it is slowing down. But if tangential acceleration is, for example, give a number, positive 3 meters per second squared. So because it is positive, tangential acceleration is positive, which means final speed must be greater than initial speed, so object is speeding up. So be careful about this. There's a sectional question about this. Also, it's a ministry exam question. If the tangential acceleration is positive, which means object is speeding up, tangential speed is increasing. If tangential acceleration is negative, the object is slowing down, which means tangential speed is decreasing. And let's give a summary about this. In fact, all these quantities, delta, theta, omega, and alpha, these three quantities are angular or rotational quantity because all they are expressed in terms of angle, radian per second, radian per second squared. Remember, we learned them all. Alpha, radian per second squared. If we multiply delta theta, angular displacement, by radius, we calculate the arc length, which is in meters. If you multiply angular speed by radius, you calculate tangential speed, meter per second. It's a linear speed. If you multiply angular acceleration by radius of the circle, you calculate the tangential acceleration, which is also a linear quantity, meter per second squared. Yani, multiply angular quantities by r, always you are going to calculate the linear quantity or tangential quantity, tangential quantity along this circular path. A question: a spinning ride at a carnival has a tangential acceleration of 0.5 radian per second squared. So this is angular acceleration, which is alpha. So it is 0.5. So record it. 0.5 radian per second squared. How far from the center is? How far from the center is defining what? Radius, of course. How from the center? So this is the center. So a ride is moving on a circle. A ride, it can be a horse, for example. How far from the center means radius. Calculate the radius. How far from the center is a rider? Whose tangential acceleration is 3.3. Yani this rider in here will have a tangential acceleration which is equal to 3.3 meter per second squared. Calculate R, but angular acceleration is also given 0.5 radian per second squared. So all are given. AT is given. Calculate R. We know that AT is equal to R times alpha. Because R is asked, you should let R alone. How? By dividing alpha. Divide by alpha both sides. Divide alpha, sorry, I wrote alpha. We should write alpha. Alpha. So this alpha and this alpha will simplify. R is going to be as AT divided, R is equal to AT divided by alpha. AT divided by alpha. So we know what AT is, tangential acceleration is. So we calculate in here. AT is given as 3.3. Alpha is given as 0.5. So AT 3.3. Alpha is 0.5. Divide them, which is equal to 6.6. Yani this ride is at 6.6 meter from the center of the right. Center of the right. This is the solution of this problem.